Hello and welcome back to the second part of op-amps. Just going to do a quick summary of what was covered in the previous video, and in this video we'll be looking at different kinds of op-amps, applications of them, and some circuit simulations of them for better understanding. Let's get right into it. So in the last video we covered the inverting side of op-amps. We also talked about a bit of negative feedback and what the op-amp does. But to refresh your memory, I would just like to bring you the equations. So for the inverting amplifier, we have the final equation of minus R2 over R1. And for the non-inverting amplifier, we have 1 plus R2 over R1. So these will be the gain that you will get from these different amplifiers, the equation you use to find out the gain. And just a quick reminder what negative feedback is. It is the feedback looping back into the inverting pin, providing feedback voltage into the pin, allowing for the use of amplified signals as opposed to max saturation swings with the amplifier. If you do remember, one of the rules is that the op-amp will do its best to maintain a 0 volt difference in between the inverting and non-inverting pin. So we'll get looking into the non-inverting amplifier now. With a non-inverting amplifier configuration, I've put some voltage probes here, as we are using multi-sim as per usual. We have a AC signal going in, and we have a voltage output that is measured. So if you remember our equation, 1 plus R2 over R1, this will be our feedback resistor coming in here. This is our resistor to ground. So do some quick maths. We got 1 plus 10 over 5. We get 2, 1 plus 2, 3. That's our gain. And with 3 times 5 for our gain, we should get 15 volts output. And I'm going to run the simulation. You see it's switching in between. We'll switch over to the graph and pause that. As you can see, we are getting a 15 volt output. So 5, negative 5, negative 15, 15. Also do realize with the non-inverting amplifier, our signals are in phase with each other, in comparison to the inverting amplifier where we were out of phase. So that was because the negative sign was there in front. So minus R2 over R1. So if we had the inverting amplifier, our output would be, this is positive, our output would be negative, positive, negative, positive. So complete opposite to our input signal. So moving on to the different configurations we can have with these op-amps and to what they can do, I'm going to go over for them as we can do mathematical things with them. In this configuration I have it as a summing amplifier, and it's where, as the name suggests, we have all these voltages added together and produced. Do take note though, there is gain with them, so just have to be aware of that, but we'll solve this anyway. Excuse me. So we have the formula here for the inverting amplifier, because if you take a look at this, we have our non-inverting pin connected to ground, we have the negative connecting to these 2 voltage sources through resistors, and this does resemble an inverting amplifier. Sorry again. Do apologize. So we can find this out by substituting each one into this equation, and we'll be able to find out what our total voltage is. So let's find our gain. Let's call this A1, A2. So for A1, we have RF over Rin. So we have minus 10 over 1. That equals to minus 10. Let's do A2. That equals to 10 over 2. We get minus 5. That's a pretty poor -5 right there. Now to find our V out. So how do we find this? Well, we multiply this by our inputs, by our input voltages, and just add them together, as that is what the summing configuration is doing. So let's do this over here. We have V out equals, we'll write the equation as V1 plus A2 times V2. I used to always do these arrows in secondary school, and that's just it just made me remember, really. It was, yeah, I used to get marked on the paper saying stop doing a treasure map and things like that. My work was very messy, so please do not follow this when you are doing calculations. You want your work to be readable by others and things like that for traceability and other things. You might even forget how you work, because I look back at my past papers and I just thought, what are you doing? What are you doing? But anyway, we'll continue on. Let's just decide we'll carry on with this. V out equals, so we're substituting our numbers here. 2 millivolts, so 2 times 10, those 2 times 10 power negative 3. So we want to input in your calculator, plus 95. I'm just going to put that there, but we are multiplying that times 5 and V. I should put a bracket there, really. And you want to put that all into your calculator. What you should get is minus 4.5 MV. This is what we will get at the output over here, minus 4.5 V. Like I said, we're gonna put this into multisim now to see if our theoretical evaluation matches with the simulation. So we're in multisim, built the circuit. I'm running it as we speak, and here we go. Got 2 MV going in, 5 MV. I should say millivolts, whatever. And I've got minus 44.996 millivolts. We'll round that up, say minus 45, just like our calculation, so we know that is correct. And of course, you can add on, keep adding voltages on and on and on, do your calculations, and this is how you would work it out. Very, very useful. In this configuration of our op-amp, we have it as a differential amplifier where we can find the difference between the two voltages and have them outputted at our output. This is the formula we use. We have V out equals R3 over R1 multiplied by V2 minus V1. I've done the calculations here already for you, and notice that we have some gain with our feedback resistor of R3 over R1. So as you notice here, we have feedback, and we do that. So this formula is for when R1 equals R2 and R3 equals R4. So as you can see, 10K, 10K, 22K, 22K, R1, R2, R3, R4. I have not labeled them. We'll solve this. 22 over 10, we get 2.2. Now we do our subtraction. 4 V2 minus 3.6 V1, we get 0.4. Multiply these two together, we get 0.88 volts. Now, we're going to run this in multi-sim now to check with our theoretical answer. So we have our differential amplifier here in multi-sim. I'm going to run the circuit real quick. As you can see, we get 879.99 millivolts. Around the cell we get 880 millivolts. And this directly corresponds with our theoretical value of 0.88 volts. So our theoretical value checks out with our simulation. The circuit or some working out here, but you soon to see that we can even use op-amps for integration purposes. And what this allows us to do is we can make oscillators in different shapes of waveforms, which when you think about it, that's quite a lot of potential that we could do with them. And I just want to explain a bit more. The negative symbol here indicates a 180-degree phase shift, and because of the output signal and because of the input signal by being directed connectly to the inverting input of the op-amp, we get a 180-degree phase shift. And I'm going to show this in multi-sim as it's much more easier to explain. You get a visualization. Here running the integrative circuit, everything like that. We have our resistor, our capacitor. This is a standard integrated circuit. And we also have the resistor here in parallel to the capacitor, as this provides a DC feedback for stable biasing. You don't really know much what's going through just for these numbers, but very interesting, we have a square wave going in. We take a look at the graph and we get a triangular, like a sawtooth wave, I believe it's called. So I'll just call it a triangle wave. But yeah, this is the integration of our square wave. We get a completely different waveform. It's very, very cool stuff, very interesting stuff. So you can just see the amount of applications we have for this, and like function generators and things. Very cool stuff. And so I'm hoping you start to see now that the vast potential of op-amps for mathematical purposes. But also you may be wondering how you can implement these in your own circuits. So do keep that in mind. We're going to move on to the last one, the differential amplifier. Last but not least, the differential amplifier. What is it? It produces a voltage output which is directly proportional to the input voltage rate of change with respect to time. Just a lot to take in. Well, essentially, it means where there is a faster or larger change of the input voltage signal, this causes a greater current, so the output voltage change will also be greater in this response. This will become more of a spike in shape when this change occurs. Again, I have not drawn the circuit, as it's much better to see in multi-sim, which I will display with these kind of things. Again, we do have the minus sign here, so do keep in mind we have a 180-degree phase shift. And yes, I will just show you this in multi-sim. So here we have our differentiator circuit and have our capacitor, resistor. So the compensation resistor can be placed at the inverting terminal along with the compensation capacitor in parallel to the feedback resistor. These two components help to alleviate both stability and noise problems, which are then be allowed to be corrected. So enough of that. We'll run this. It's took us straight to the graph here. So we have a sawtooth triangle waveform going in. When we find the differential of that, and we get a square wave, the complete opposite of our circuit before. As mentioned before, we have a 180-degree phase shift. It's going up here, down, down, up. And yes, so as you can see, we can do mathematical functions with these amplifiers. Very, very cool stuff. I end off the video here as I think it's gone a bit too long for what I would like it to do. I do want to keep these type of lessons short and easy to digest and not cramming too much information at one time. Make it feel like a university lecture. Just one last note, I want to speak about positive feedback. So in the last video I did speak about negative feedback. So you might be wondering, is there positive feedback? And short answer, yes there is. And this is where we send our feedback to the non-inverting pin of our op-amp. A very positive benefit of this is that another additional use of op-amps is we can make comparators. And with the adjustment of our feedback resistor, we can do something called hysteresis. And what this intends to have the effect of is it gives us two threshold voltages instead of one. And this is what we call the hysteresis voltage. So you might see something like that before. You know, that's your hysteresis voltage in between. But essentially what you want to do with this information is that maybe you have a noisy signal or just a random signal going in, boop, 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 boop. There's your baseline. You want to say, I would like my comparator to produce an output when the signal passes here. So you get the signal pass by here, and we get the output, the saturation output, going flat line. The hysteresis though, output when we make Schmidt triggers and things, we get two voltages. We have feedback. And this helps us alleviate from noise because, you know, we do get noisy signals. Maybe it'll be a false alarm, so you might get like a little noise here, then a real signal, then a little noise there, a real signal, a little noise, like a little noise real. You know, we don't want these noisy parts. We hate them. So we made the Schmidt trigger to hopefully it's not cancelling out, but like we get a more accurate result into what we're sending to the output to make sure we don't get false true results or false outputs essentially. And I will speak more of this in the next video. I did say I was going to go over the different types of op-amps and things like that and the characteristics, but I'm looking at my notes here, what I wrote down and planned, and it's looking a bit too much to fit into one video, so do it in the next video and that will hopefully give us a nice little summary of what we've done for op-amps so far. So, that's good. Hope you've learned something, hope it's been good, and I'll see you in the next video. Take care.